Good evening. This is Glomerular Filtration and Forces. My name is Hannah Antosh. This presentation is for Dr. Brittany Smith in Biology 515, Human Anatomy and Physiology 2, on to the urinary system. There we go. So, glomerular filtration occurs when fluid is filtered from the glomerulus into the Bowman's capsule. When fluid is filtered from the glomerulus into the Bowman's capsule, it must pass through three distinct layers. And those three layers make up the glomerular membrane. So the first one is the glomerular capillary wall, then we have the basement membrane, and then we have finally the inner layer of Bowman's capsule. These layers act as a filter to allow water, H2O, and small solutes through while not allowing blood cells and plasma proteins through. And this is very important. We'll talk about what happens when plasma proteins are allowed through by an accident later. So the first layer is the glomerular capillary wall. So this is comprised of a single layer of endothelial cells that are kind of pancake shaped. Okay, they're not big fluffy cells. They're just a single layer of flattened pancake like cells. When I want my daughter to not run off in a parking lot, I tell her, hey, don't run off or you'll be a pancake, right? Because pancakes are flat, similar to these endothelial cells. The glomerular capillary wall is actually full of what we would call kind of like holes. Think like a strainer. So if you're going to go make pasta, you're going to pour your pasta into a strainer to allow the water out, but keep the pasta, hopefully, in. And this actually allows this capillary wall to let more water through and more solutes through than any other capillary systems in the body. And this is important. We'll see those little spaces right here in between each of these endothelial cells. Next up, we have this basement membrane, which is this yellow section right here on the diagram. This basement membrane is acellular, meaning that it has no cells. It's actually comprised of collagen and glycoproteins, which gives it a gelatinous consistency to it. Collagen plays a structural support in this membrane. Remember that collagen is an incredibly important protein for structure, support, and it's been widely touted by the health and beauty industry lately as being kind of almost like a medical miracle in a way. But collagen is very important. It's also made up of glycoproteins, like I said, which work to actually filter out the smaller plasma proteins, right? The large plasma proteins physically cannot fit through there, but smaller ones can. It's actually the pore space in that glomerular basement membrane right here. That pore space is actually just barely big enough for albumin. Is it big enough for albumin? Yes, it is. Just barely, but this would actually be quite a large problem, right? We don't want albumin going through and making its way into the Bowman's capsule. So what actually happens is that this gelatinous layer right here and the albumin both happen to be negatively charged. Now, if we think back to a chemistry class, any chemistry class, we'll learn that opposites attract but like repel. So because both this basement membrane and albumin are negatively charged, they will actually repel each other, which aids this membrane in strongly discouraging, I would say, albumin from passing through. So because of these things, A, because the pore space is so small, and B, to the similarly charged particles, very few plasma proteins make it through. Some do, but very few. Now, the final layer is the inner layer of Bowman's capsule. right out here. This actually contains podocytes. Now, remember that podo means, is Greek for the word foot. I happen to take a couple years of Greek in Bible college. This is how I know that. But podo means foot. And what happens is that these little podocytes are cells that have multiple quote unquote feet. And these feet surround that glomerular tuft. And then the narrow slits in between each of these foot cells create what we would call a filtration slit, seen right here. Right, these little cells right here, these podocytes on the diagram are not necessarily a great representation of how they would look in real life, because it's very difficult to really show how they are kind of hugging that glomerular tuft. But just rest assured that they are. And then this filtration slit right here is about 40 nanometers large. It actually creates a pathway that fluid, can use to leave the capillary and finally enter into the promised land that is the Bowman's capsule. Now, the force. If this were one of my classes that I was teaching, I would make a great Star Wars joke right here. Now, something must drive the plasma within the glomerulus into the glomerular membrane. So it's not going to use local energy. It's not really going to use like active energy. It's not going to be something that's going to use like ATP. However, it will use what we would call a passive physical force. So physics really is what's pushing this fluid and was really what's driving this process. The principle that applies here for the fluid movement is really quite similar to the principles that guide the other capillaries' fluid movement, with two main contrasts. The first being that the glomerular capillaries are far more permeable than other capillaries due to their enlarged pore space comparatively. The second thing, and the big thing, is that in the glomerular capillary, filtration is occurring across the entire capillary. Typically in capillaries, what we'll see is that filtration happens at the beginning of the vessel and reabsorption will occur at the end of the vessel, which is not the same here, because in the glomerular capillary, filtration is occurring across the entire capillary. Now, there are three main forces at work in this fluid movement. The first is called the glomerular capillary blood pressure. The second is the plasma colloid osmotic pressure. And finally, Bowman's capsule hydrostatic pressure. Now, the glomerular capillary blood pressure is the fluid pressure that blood is exerting when it's held within those glomerular capillaries. This pressure is dependent upon the heart's contraction relaxation cycle, so it depends on the heartbeat. And it also depends on the blood flow into the afferent and efferent arterioles. The pressure here is going to be about 55 millimeters Hg, whatever that happened to mean, which makes this actually higher than other capillary pressures. Between the three forces that are moving the fluid, this one is the highest. And that's because the afferent arterioles are larger than the efferent arterioles, which means blood is moving in quite quickly, but it is not leaving as quickly as it's coming in necessarily, which is actually creating kind of like a buildup. So like if you've ever gone to go merge on the freeway, and we have them here on the West Coast, but we'll have a stoplight to get onto the freeway, right? And it'll allow like one car at a time. And so what happens is, during rush hour, you have 100 cars trying very hard to get onto the freeway, but they're stacking up faster than what this stoplight will let them go through. And so it's creating quite a bit of pressure at the entrance to the freeway. And the same thing's happening here. Blood is coming in more quickly than it's able to leave. And due to this pressure, fluid is able to be pushed from that glomerulus into the Bowman's capsule. This is kind of the big boy of the three forces. This one kind of does the most work. Now, the second force is the plasma colloid osmotic pressure force. Now, this is going to occur because the plasma proteins are not equally distributed across that glomerular membrane. They're not equally dispersed, right? Because remember that these plasma proteins cannot pass that gelatinous layer that we just talked about. And so they're going to stay they're going to stay in the glomerulus. They're going to stay in those glomerular capillaries. They should not be able to pass into the Bowman's capsule. And so what happens is then we have tons of solutes on one side and few solutes on the other side. Now, if we think back to any freshman biology class in any freshman lab, we'll remember when we do some kind of lab on this. Could be the egg lab where you put an egg in water and watch it swell, or I do gummy bears in water, right? So we have lots of a high concentration of solutes in the gummy bear and a low concentration of solutes in the water, right? And then as we think about it, right, water is going to move from areas of high concentration to areas of low concentration. So water is going to move from that Bowman's capsule into the glomerulus. It's going to move from that area of high concentration to an area of low concentration, from less solutes to more solutes. And that's actually going to create an opposing force that's about 30 millimeters Hg. And then finally, we have the Bowman's capsule hydrostatic pressure. Now, this is the smallest of the three forces at only about 15, and this just pushes fluids out of the Bowman's capsule. This one kind of does not the least, well, maybe the least amount of work. Of the three, this is kind of like the baby bear. Doesn't really do as much as the other two. Does some, but not as much. Now, I wanted to kind of call us back to earlier when I was talking about albumin. So, a real-life application of this would be something called albuminuria. And this occurs when albumin is coming through in the urine. Okay, so this can occur if the charges are disrupted in that basement membrane, and the basement membrane is no longer able to kind of shoo the albumin away, and it's being allowed through more albumin is being allowed through than what is ideal. It can create albuminuria. And now, this is a issue. This can cause several things, or can be a biomarker for several diseases such as chronic kidney disease, cardiovascular disease, coronary artery disease, strokes, heart failure, and microvascular disease. This is not good. Now, can albuminuria, protein can appear in the urine after exercise or just a little bit normally, but when it occurs in large amounts, that is quite concerning from what I read. Thank you so much.